The universe is a vast, dark ocean. For centuries we have stood at its shore, peering out with our eyes, then with telescopes, each one a little better than the last. We've been trying to see back to the very beginning, back to the first light after the cosmic dawn. We call this beginning the Big Bang, a moment of incredible energy and creation almost 14 billion years ago. We thought we had a pretty good story of what happened next, a story of slow, graceful growth, a story where tiny specks of matter gradually clumped together over hundreds of millions of years to ignite the first stars and form the first baby galaxies. It's a good story. It makes sense. But what if the story needs a new chapter? The James Webb Space Telescope is our most powerful time machine yet. It's a magnificent instrument, a golden eye designed to capture the faintest, oldest light in the cosmos. And in the summer of 2025, it stared into the blackness and saw something that sent a jolt of astonishment through the scientific community. It found things that, according to our story, shouldn't be there, at least not yet. NASA scientists, people who have spent their entire lives studying the heavens, found themselves looking at images that were both beautiful and bewildering. This wasn't just another incremental discovery. It felt like finding a fully grown oak tree in a garden where you had only just planted the seeds a week ago. Imagine you're an archaeologist digging in the dirt. You expect to find simple tools, maybe some pottery shards from an ancient primitive culture, but instead, you unearth a smartphone. That's the feeling astronomers at the University of Missouri got when they looked at JWST's latest data. They were looking for the cosmic equivalent of simple tools, faint, small, barely there proto-galaxies. Instead, they found nearly 300 objects that were shockingly bright, incredibly massive, and looked far too well developed for their age. It was a cosmic surprise party, and we were the guests of honor, left scratching our heads and wondering if we had misunderstood the invitation. This discovery doesn't just add a new detail to our understanding of the universe, it pulls at the very threads of our most fundamental theories. It asks us to reconsider how quickly the universe got up and running. How fast did the cosmos mature from a hot, dense soup of particles into the grand, star-spangled tapestry we see today? The James Webb Space Telescope wasn't just built to confirm what we already knew. It was built to challenge us, to show us the things we couldn't even imagine. And with these latest findings, it has delivered on that promise in the most spectacular way, opening a new, exhilarating, and deeply puzzling window on the dawn of time itself. To find these cosmic mysteries, the James Webb Space Telescope had to perform an incredible feat of cosmic observation. Think of it like trying to spot a single candle flame on the surface of the moon. The light from the universe's first galaxies has been traveling for over 13 billion years to reach us. As it journeys across the expanding fabric of space-time, its light gets stretched out, shifting from the visible light we see with our eyes into the longer wavelengths of infrared light. Our atmosphere blocks most of this ancient infrared light, which is why we had to send a telescope like Webb into the cold, dark vacuum of space, a million miles from Earth, to see it clearly. There, unhindered by our planet's glow, Webb used its powerful instruments, specifically the near-infrared camera, NIRCam, and the mid-infrared instrument, or MIRI, to conduct a deep survey of the sky. It stared at a tiny patch of the cosmos for nearly 100 hours, gathering every single photon of light it could. Researchers led by Haojing Yan and Bangjung Tom Sun from the University of Missouri then used a clever trick called the dropout technique. They looked at the images through different colored filters. Extremely distant objects, because their light is so stretched, will show up in the reddest infrared filters but will completely vanish, or drop out in the bluer ones. It's a cosmic game of hide and seek that only the oldest things in the universe can play. This technique allowed the team to sift through a cosmic haystack of billions of stars and galaxies to find the needles they were looking for, candidates for the most distant galaxies ever seen. It's a painstaking process, requiring immense computational power and a keen eye for detail. The scientists were essentially creating a cosmic core sample, drilling down through billions of years of universal history. They were hoping to find a few faint smudges, the seeds of today's grand spiral and elliptical galaxies. The expectation was to find things that were small, disorganized, and dim, reflecting the universe in its absolute infancy, just a few 100 million years after the Big Bang. But the universe, as it often does, had other plans. The dropout technique worked beautifully, perhaps too beautifully. It didn't just reveal a handful of faint objects. It unveiled a treasure trove. The final count was staggering, nearly 300 candidates for ancient galaxies, all shining with an intensity that defied explanation. These weren't just smudges, they were brilliant points of light. The discovery, published in the Astrophysical Journal on June 27, 2025, wasn't a quiet announcement. It was a thunderclap that echoed through observatories and university physics departments around the world, signaling that our view of the early universe was about to change forever. So what exactly are these 300 bright objects that have caused such a stir? The simplest and most profound answer is that they appear to be some of the very first galaxies our universe ever created. These are not the nearby, well-behaved galaxies like our own Milky Way or Andromeda. These are pioneers from the cosmic frontier, existing at a time when the universe was less than 1 billion years old, a mere toddler in cosmic terms. They are like ancient fossils of light, carrying secrets from a time we have only ever been able to imagine. Their light has been traveling towards us for more than 13 billion years, a journey that began when the universe was shrouded in a dark neutral fog. What makes them so mysterious is their sheer brightness and apparent size. According to our established story of cosmic evolution, the first galaxies should have been small and dim. They would have formed from the first tentative gatherings of gas and dark matter, slowly igniting their first generation of stars over vast timescales. These early galaxies were supposed to be the cosmic building blocks, the little bricks that would later merge over billions of years to construct the grand galactic structures we see today. But these 300 objects don't look like bricks. They look more like fully formed buildings, shining with the light of billions of stars that somehow came together in a cosmic flash. Scientists are considering a few possibilities to explain this unexpected brilliance. One idea is that these objects are galaxies experiencing an intense and short-lived burst of star formation, known as a starburst. Imagine an entire galaxy's worth of gas collapsing and igniting into stars all at once. This would make them incredibly luminous for a brief period. Another more exotic possibility is that they contain something we haven't accounted for. Perhaps they are powered by supermassive black holes at their centers that formed much, much earlier and grew much, much faster than our theories allow, creating blazing quasars that outshine their host galaxies. Each possibility presents its own set of challenges to our current understanding. The truth is, we don't yet know for sure what they are. Right now, they remain candidates. They are tantalizing clues, but not yet proven facts. Each one of these 300 dots of light is a riddle posed by the universe. Are we looking at a new type of celestial object we've never seen before? Or are we seeing a familiar process, galaxy formation, that happened in a way that was far more violent, rapid, and efficient than we ever thought possible? Answering this question is now one of the most urgent tasks in modern astronomy. These 300 cosmic riddles are not just curiosities. They are signposts pointing toward a new and perhaps revolutionary understanding of our cosmic origins. The prevailing theory of our universe's origin is the Big Bang model. It's important to clarify that these new discoveries do not mean the Big Bang didn't happen. The evidence for a hot, dense beginning, like the cosmic microwave background radiation and the expansion of the universe, is overwhelming. However, the Big Bang model is more than just a single moment of creation. It includes a detailed timeline of what happened afterward, a story known as the Lambda CDM model. This story describes how gravity, acting on dark matter, the CDM part, and influenced by dark energy, the Lambda part, slowly sculpted the universe we see today. It is this part of the story, the what happened next, that is being challenged. Our models of galaxy formation are built upon this timeline. They predict a bottom-up process. After the Big Bang, the universe was incredibly smooth, with only tiny fluctuations in density. Gravity would have worked on these tiny, dense spots first, slowly pulling in gas and dark matter to form small structures. These small structures would then merge over eons, growing into larger and larger galaxies. Think of it like a fine mist slowly condensing into tiny droplets, which then merge to form bigger drops, and eventually puddles and lakes. This process is supposed to take time. The models predicted that the first truly massive, bright galaxies shouldn't appear until at least 1 billion years after the Big Bang. Herein lies the problem. The 300 objects discovered by JWST appear to exist much earlier than that, some perhaps as early as 500 to 700 million years after the Big Bang. And they are not small and dim, they are big and bright. It's like our cosmic timeline is out of sync. It's as if the universe skipped a few steps, jumping from a fine mist directly to large puddles without passing through the droplet stage. This suggests that either the ingredients for building galaxies were more readily available, or the recipe for cooking them up was far more efficient than we calculated. The universe, it seems, was in a hurry to get the lights on. This forces scientists to ask some profound questions. Does dark matter behave differently than we thought, allowing it to clump together faster in the early universe? Did the first generation of stars form and die in a way that produced heavy elements much more quickly, providing the raw material for the next generation of stars to form in brilliant bursts? Or is there a fundamental aspect of gravity or cosmic expansion in the early universe that our Lambda CDM model is missing? These are not small tweaks. Answering any of these questions could lead to a significant revision of the standard cosmological model, adding a major new chapter to our story of the cosmos. The core of the issue can be summarized in a simple phrase: too big, too soon. Our understanding of the universe is built on physical laws and models that dictate the pace of cosmic events. These models have been incredibly successful at explaining the universe as we see it today and in the relatively recent past. They set a kind of cosmic speed limit on how fast things can grow. For a galaxy to form, you need to gather an immense amount of matter, gas, dust, and dark matter, into one place. Gravity is the engine that does this work, but gravity, for all its power, takes time to pull things together across vast cosmic distances. The universe needed time to cool down, and for matter to start clumping. Imagine trying to build a giant skyscraper in just 1 week. It's impossible. You need time to lay the foundation, erect the steel frame, pour the concrete, and install all the systems. Our cosmological models have similar construction timelines for galaxies. They tell us that building a massive galaxy, brimming with billions of stars, should take hundreds of millions, if not billions of years. The discovery of these 300 bright candidates is like finding a whole city of fully built skyscrapers in a place and time where we expected to see only construction sites with foundations barely laid. It fundamentally challenges our assumptions about the cosmic construction schedule. This too big, too soon problem forces us to look at the very beginning of the process. The seeds of these galaxies were the tiny density fluctuations present in the universe just after the Big Bang. Our standard model assumes these fluctuations were of a certain size, but what if they were bigger than we thought? If the initial seeds were larger, then gravity would have had a head start, allowing it to accumulate matter much more rapidly. This would be like starting your skyscraper project with a pre-built foundation and a huge stockpile of materials already on site. It would drastically speed up the construction time. This possibility would require us to adjust our measurements of the primordial universe. Alternatively, the physics of the star-making process itself might be different in the early universe. Perhaps the first generation of stars, forged from pure hydrogen and helium, were incredibly massive, hundreds of times the mass of our Sun. These behemoths would have lived fast and died young, exploding as spectacular supernovae that compressed the surrounding gas and triggered furious new waves of star formation. This could create a runaway chain reaction, building up a galaxy's stellar population at a blistering pace. This scenario doesn't change the initial conditions, but rewrites the rules of galactic assembly, suggesting a process that was far more explosive and efficient than the slow, steady growth we had envisioned. For over 30 years, the Hubble Space Telescope was our premier eye on the cosmos. It gave us breathtaking images and revolutionized our understanding of the universe, including the iconic Hubble Ultra Deep Field, a long-exposure image of a tiny patch of sky that revealed thousands of distant galaxies. Hubble looked primarily in visible and ultraviolet light, with some limited infrared capability. It showed us galaxies as they were billions of years ago. But Hubble, for all its power, had its limits. It couldn't see the very oldest, most red-shifted light from the era of the first galaxies. It was like trying to hear a whisper from across a crowded room. It could only catch the loudest voices. The James Webb Space Telescope is a different kind of instrument altogether. It was specifically designed to be Hubble's successor for this very task. Its primary mirror is over 6 times larger in area than Hubble's, allowing it to collect far more light and see much fainter objects. More importantly, It is optimized to see in infrared light. This is the key. The expansion of the universe stretches the light from the most distant objects so much that by the time it reaches us, it is no longer visible light but infrared. JWST, with its giant golden mirror and super-sensitive infrared detectors, can hear that cosmic whisper. It can see the very things that were invisible to Hubble. When JWST re-examined the same patch of sky as the Hubble Ultra Deep Field in a survey called MIDIS, the MIRI Deep Imaging Survey, the difference was astounding. The new image was the deepest mid-infrared picture of the universe ever taken. Where Hubble saw a certain number of galaxies, Webb saw those and 2,500 more. It was like putting on a new pair of glasses and suddenly seeing the world in stunning high definition. Many of these newly found objects were extremely red, the telltale signature of being incredibly ancient and distant. Webb didn't just add to Hubble's picture, it revealed a whole new layer of reality that was hidden just beneath the surface. This leap in capability is why Webb is making these paradigm-shifting discoveries. It's not that Hubble was wrong, it's that it couldn't see the whole picture. Hubble showed us the teenagers and young adults of the galactic population. Webb is now showing us the infants in the cosmic nursery. The comparison between their images makes it clear. We are in a new era of astronomy. The 300 mysterious objects and the thousands of other ancient galaxies being found were simply too faint and too redshifted for Hubble to detect. Webb has opened a new cosmic frontier, and we are its first explorers. Discovering 300 potential ancient galaxies is an exhilarating moment, but in science, discovery is only the first step. The next, and arguably most important step, is verification. Right now, these 300 objects are candidates, identified based on their color and brightness in images. This method, while powerful, can sometimes be fooled. For instance, a closer, less exciting object that is simply very dusty can mimic the red color of a very distant galaxy. To be absolutely certain, scientists must move from taking pictures to doing something called spectroscopy. This is the gold standard for confirming cosmic distances and compositions. Spectroscopy works by breaking an object's light down into its constituent colors, like a prism creating a rainbow. Within this rainbow or spectrum, there are dark or bright lines called spectral lines. These lines are like cosmic barcodes. They are created by different chemical elements which absorb or emit light at very specific wavelengths. By analyzing the pattern of these lines, astronomers can tell what an object is made of. Crucially, they can also measure how much these lines have been shifted towards the red end of the spectrum. This redshift measurement gives a precise calculation of the object's distance and therefore its age. This process is incredibly time-consuming and difficult. These objects are unimaginably faint. To get a clean spectrum from a single one of these candidates, the James Webb Space Telescope might have to stare at it for many, many hours. Given that telescope time is a precious resource shared among thousands of astronomers worldwide, studying all 300 candidates this way will be a long-term project, likely taking years to complete. As of today, August 25, 2025, scientists have successfully performed detailed spectroscopy on just one of the 300 candidates, confirming that it is indeed an ancient galaxy from the early universe. This one confirmation is a huge victory and gives great confidence that many others in the sample are real as well. But the work must continue. Each new spectroscopic confirmation will add another piece to the puzzle. Scientists will analyze the data from each confirmed galaxy to understand its mass, its rate of star formation, and its chemical makeup. They will look for patterns. Are all of them absurdly massive? Do they all have similar chemical signatures? The scientific community will debate the results, challenge the interpretations, and run new simulations to try and explain the findings. This is how science progresses, not through a single eureka moment, but through a slow, careful, and collaborative process of gathering evidence, testing hypotheses, and building a more accurate picture of reality, one confirmed galaxy at a time. When a discovery this big comes along, it's natural for our imaginations to run wild. The idea that these strange objects could be defying physics or are evidence of another universe is incredibly exciting. It taps into our deepest curiosities about the unknown. However, it's crucial to separate thrilling speculation from the actual scientific evidence. As of now, none of the published papers or statements from the researchers involved suggest that JWST has found evidence of a multiverse or seen anything that breaks the fundamental laws of physics as we know them. The universe is still playing by the rules. The issue is that we might not have the complete rulebook yet. What we have found are not windows into another reality, but rather unexpected new features within our own universe. These 300 objects and others like them are part of our cosmic history. They are our ancestors. The surprise comes not from them being alien in the sense of belonging to another cosmos, but from them showing us that our own universe's youth was far more dramatic and precocious than we had imagined. It's like finding a diary from your great-great-grandparent and realizing they lived a life far more adventurous and complex than the simple stories passed down through the family. The person is still your ancestor, but your understanding of them, and by extension yourself, is now richer and more complex. The challenge is not to physics itself, but to our models of physics and cosmology. A model is our best attempt to describe reality based on the evidence we have. The Lambda CDM model has been our standard model for decades because it has explained so much, so well. But like any model, it's a simplification. When new evidence comes along that doesn't fit, it doesn't mean reality is broken. It means our model is incomplete. This is a normal and healthy part of the scientific process. Einstein's theory of relativity didn't prove Newton's laws of gravity were wrong. It showed they were an incomplete description that worked well under certain conditions. So while the idea of another universe is a fascinating topic for science fiction, the reality of this discovery is, in many ways, even more profound. We are being forced to reevaluate the story of our own home. We are learning that the conditions in the very early universe may have allowed for processes we haven't yet fully conceived. We are not visitors looking into a strange new world. We are inhabitants of this universe, finally getting a clearer picture of our own origins. The surprise isn't that we found something alien, but that we are learning something so fundamentally new about ourselves and where we come from. The discovery of these 300 mysterious objects by the James Webb Space Telescope is not an end to a story. It is the explosive beginning of a new one. We stand at a thrilling crossroads in our cosmic journey. For decades, we have been building a grand narrative of the universe, and now we have found a major, unexpected plot twist right near the beginning. This is not a cause for despair, but for excitement. This is what science is all about: the joy of the unknown, the thrill of the puzzle, and the humility to recognize that the universe will always be more clever and more surprising than we can imagine. These findings will ignite a new wave of research and exploration for years, even decades, to come. Theorists around the world are already scrambling back to their blackboards, running new computer simulations, and tweaking their models to see if they can create a universe that grows up this fast. Observers will be writing proposals for more telescope time, eager to perform the detailed spectroscopic follow-up needed to confirm these candidates and search for even more. Every new data point will help us refine our story, to choose between the competing ideas. Were the initial seeds of structure bigger? Was star formation more explosive? Is there new physics at play? Discoveries like this matter because they speak to one of the most fundamental human questions. Where did we come from? The story of galaxy formation is the story of our own cosmic heritage. The atoms in our bodies, the carbon, the oxygen, the iron, were forged inside stars that lived and died within galaxies. Understanding how the first galaxies formed is, in a very real sense, understanding the first step in the long chain of events that ultimately led to our planet, to life, and to us. When we look back to the dawn of time, we are looking at the origins of our own existence. The universe does not give up its secrets easily. It challenges us, it teases us, and it forces us to be better, smarter, and more creative. The James Webb Space Telescope is our latest and greatest tool in this grand quest for knowledge. It has opened a new window, and the view is more spectacular and more puzzling than we could have hoped. The adventure is just beginning. There are more mysteries to solve, more light to gather from the darkness, and a whole new chapter of the cosmic story waiting to be written. And we are the generation that gets to write it.